Okay, picking up where we left off just a little bit ago. For our ionic compounds, we also have an additional feature called lattice energy. So the formation of ionic compounds is usually exothermic. It produces energy, releases energy. And this funky equation that we've got here is written in this funky way because of this little zero or the degree sign thing, right? What does that mean? Anyone remember that little zero? Standard. So this is our standard enthalpy of formation. And our standard enthalpy of formation can have these 1/2 in front for coefficients. The ionization energies and electron affinities don't completely explain why this is so negative. Our first ionization energy for sodium, it takes some energy. We have to put in energy, 496 kilojoules per mole. Our electron affinity for chlorine is minus 349 kilojoules per mole. So that predicts that we have to put in 147 kilojoules per mole in order to get the electron to transfer. But we know that it's minus 400. So where does that extra energy difference come from? It's the lattice energy. So the lattice energy is the energy associated with the formation of a crystalline lattice. A lattice like a repeating grid or framework of, in this case, cations and anions. We'll see some images, I think, of those in the next couple slides. When it comes together, the opposite charges come together, and that causes a lowering of the energy. Lower energy means stability. It's more stable when the positive and negative charges come together. And that extra energy is released as heat. They kind of lock into place. It's the way you can think of it. I've never had like a clump of magnets or magnetic marbles that was big enough that you could just like throw them together and they would just all clump together like when you shake them. But that's what I imagine this is sort of like. A bunch of little marbles that are magnetized. You throw them all together, you shake it around, and eventually they would lock into a sort of grid. So that's what's happening here. So it's not just because of, they are exothermic, this second point. Formation of ionic compounds isn't exothermic because of the metal wanting to lose an electron and the nonmetal wanting to gain an electron. It's exothermic because when the cation and anion coalesce to form a lattice is very stable. So here is what that lattice might look like. On the left, we've got our gaseous ions that are coalescing. I like the blurriness of it. It makes me feel like I'm not focusing. They're all coming together. And then, boom, they form this beautiful lattice, repeating negative and positive charge grid in 3 dimensions. A crystalline structure. And heat is emitted. That's due to the lattice energy. So that's the lattice that we've been talking about. Any questions about the lattice before we move on to the beloved Born-Haber cycle? All right, the Born-Haber cycle is a way to calculate lattice energy. So we can take a hypothetical, theoretical, a not real, a predicted, a projected series of steps. All of those delta H sub F with the little 0, the degree thing, those standard enthalpy of formation. We'll pick up a bunch of those. And from these standard enthalpy of formation equals 0 states, we're going to construct the ionic compound. We also need to know the overall change in enthalpy. So what we're looking for with this is the lattice energy. We're looking for that extra stability because of the crystalline lattice, because of the positive and negative charges just being so comfy and cozy next to each other. That's what we're looking for here. And we're going to compare our Hess's law product, our standard enthalpy of formation from Hess's law with these things, and our overall change in enthalpy. The difference will be the lattice energy. So here is what that could look like. We are starting down there at the red arrow. So we're starting with sodium as a solid, because that's its normal state. We're starting with chlorine. 1/2 of chlorine is a gas, because that's its standard state, is Cl2 as a gas, and we need 1/2 of those. And we can change the sodium, the solid sodium, into gaseous sodium. So that's going to be our first step. Step 1. And then in orange, go Tigers, our next step is to turn this Cl2 into chlorine. And that takes some energy. And then I don't have yellow, so we'll skip to green. Our third step is the ionization of the gaseous sodium. So we're turning it from Na to Na+. And we can add that electron to chlorine. This step decreases energy because chlorine wants to gain that electron. So there's our step 4. And then last, we can form the crystalline solid from the gaseous ions. We don't know exactly what that step is going to look like, but we know the enthalpy change in formation from sodium and chlorine. And so by comparing these differences, or these energy changes, from our starting state to this gaseous state and our normal way of producing sodium chloride, we can figure out the lattice energy. So we're comparing those two purple bars. And the difference is the lattice energy. So that's the extra stability because of the lattice. We have some trends for lattice energy based on ion size. So the lattice energy for alkali metals with chlorine decreases as we move down the column. And the reason that the lattice energy decreases, we have less stability gained by forming the lattice. The reason it decreases is because of the size of our ions. As we move down the periodic table, our atomic size increases, getting bigger atoms. And because they're bigger atoms and they're ions, they're not covalent bonding, they're not overlapping. They're electron shells, they're sitting next to each other. Because of that, the distance between our positive and negatively charged ions is increasing. So increasing the size between them, the distance between them, changes the energy. We looked at Coulomb's law earlier. I don't remember exactly what it is off the top of my head, but I know that it had Q1, Q2 on the top, and it had like 4 pi E naught R or something like that, right? That looks familiar, hopefully. A funky looking thing. We don't really need to know what it is, but we know that the energy is inversely proportional to the radius. So that means the closer they get together, the smaller the radius, the bigger the energy is going to be. The further they are apart, the lower the energy is going to be. Any confusion about that? Or questions about stuff so far? Another factor in lattice energy is the ion charge. So if we compare sodium fluoride and calcium oxide, sodium and fluorine are both have a charge of 1. +1 or -1, or 1 plus or 1 minus should be. Calcium's a 2 plus, oxygen's a 2 minus. The lattice energy difference is drastically different. And ionic size doesn't explain the difference because they're all relatively similar in size. Not exactly, but they're similar enough. But it wouldn't cause as big of a difference. And the reason that we have this giant change in lattice energy is because of the magnitude of the charges. So that's the Q1 and Q2 that I wrote out in the Coulomb's law, whatever my brain remembered of Coulomb's law. So Q1 and Q2 are charge. And the energy is directly proportional to Q1 and Q2. So if Q1 and Q2 get bigger, so does energy. If one increases, the other increases. If one decreases, the other decreases. In this case, we're going from charges of 1 each, 1 positive, 1 negative, to 2 positive and 2 negative. So we would expect maybe a 4-fold difference in energy based on the charge alone. So higher charge has greater lattice energy. I'm writing greater because it's more negative. The magnitude of the lattice energy is increasing. Okay, so the summary of what happens, lattice energies become less exothermic with increasing ionic radius. Energy decreases. As radius increases. lattice energies become more exothermic, energy increases. As charge increases. And these are based on Coulomb's law. Or at least that's how we would predict the difference. Arrange the following in terms of increasing magnitude of lattice energy: lithium bromide, potassium iodide, calcium oxide. You're welcome to discuss with your neighbor if you'd like to. Okay, what are the two factors that affect the magnitude of our lattice energy? One of them is the radius. And what produces a stronger or a greater ionic charge is the other one. What produces a greater lattice energy? Big radius, small radius. So small radius is bigger magnitude. What about for charge? Does a small charge or a big charge produce a larger lattice energy? Yeah, bigger charge, bigger lattice energy. So these are the two things that we want to be thinking about when we're comparing these three ionic compounds. Which of these two effects is larger, the radius or the charge? Charge is the bigger factor. because there's Q1 and Q2 in the numerator of our Coulomb's law. There's just R in the denominator, and the R doesn't change very much. Even if that one doubles, changing the charges, doubling the two charges, quadruples the total charge term, or whatever you want to call it. So thinking about charges, two of these have charges with a magnitude of 1. One of them has charges with a magnitude of 2. Which one has a charge with a magnitude of 2? It has the 2 plus 2 minus. Yeah, CaO is going to have, here has a 2 positive charge, the oxide has a 2 minus charge. That's going to be our biggest. Because of that charge factor. Lithium bromide and potassium iodide both have 1 positive and 1 negative charges for their metal and nonmetal respectively. So we are not comparing on charge, we're going to be comparing on radius. And we know that a small radius results in a larger magnitude. Which of these two, lithium bromide or potassium iodide, has a smaller radius between them? In red or in green? Yeah, lithium bromide is going to have the smaller radius. Lithium is smaller than potassium. Bromine is smaller than iodine. So lithium bromide has a smaller radius than Ki. That means it's going to have a stronger lattice energy. So this would be our order. Questions? All right. Ionic bonding models do help explain some of the properties of our ionic compounds. So in our model, we know that we have ions in fixed places of the solid. If you heat it up enough, they can move. But they have really high melting points because one sodium, for example, might have on every 6 sides, if you think of it like it might have 6 negatively charged things next to it. And that each of those might have 6 positively charged things next to it. So we've got our lattice array, lots and lots of neighbors kind of interacting very strongly with each other. That's going to produce very strong intermolecular forces. So we're going to have strong forces all around us. We're going to be comparing this in a second to molecular compounds. Our ionic solids also don't conduct electricity. If you put salt in a beaker and you try to run an electric charge through it, it's not really going to work out because we've got a collection of positively and negatively charged ions, but they're all completely balanced out here, and they don't move. If you put it in a solution, however, and you separate those ions, then it will produce, or it will conduct electricity. It becomes an electrolyte solution because we've separated the positively and negatively charged ions, and so they can move freely around each other. So that works. In pretty much everything else, we get covalent bonds. These are for molecular compounds. So where we just have nonmetals. In our Lewis structure, we share electrons for molecular compounds. So we can show bonding for H2O and Cl2. One way that we can do this, we start out with just a basic framework, and these are each going to have a certain number of valence electrons. Oxygen will have 6, each of the hydrogens has 1. And they can share electrons. So like H2O has this structure. Another way that we can write this out a little bit more condensed is sandwiching those electron pairs between the hydrogen and the oxygen. So something like this. This would be our Lewis structure for H2O water. For chlorine, it's a similar thing. They're going to share one pair of electrons. They have 7 valence electrons. If they share one, they get their full octets. We'll go through the steps for writing these out. So this is what bonding looks like in the structures. And we can write them as 2 dots between the symbols, or the way that we're more frequently going to see them, we can draw them in as lines. And drawing them in as lines has some advantages. For example, it helps us quickly see which pairs are bonding and which pairs are non-bonding. So our bonding pairs, we're talking about bonds, 2 or more electrons, 2, 4, 6, 8 electrons that we're using to bond between 2 atoms to connect them. And lone pairs, these aren't bonding, these are only on 1 atom. Whereas our bonding pairs are shared. So look at our octets for our H2O. Hydrogen, being so small, wants just a duet. It wants 2 electrons. Each of these hydrogens is right next to a pair of electrons, or when we draw it out with the lines, it has access to the 2 electrons in that pair, so it has a full duet. The oxygen, if we draw it with dots around it, has 8 dots around it. It has access to 8 electrons. It has its full octet. If we draw it out with the lines, it's got 2 bonding pairs. 2 times 2 is 4, right? 2 bonding pairs. And then we also have 2 non-bonding pairs, or lone pairs. Those lone pairs only count towards the octet for oxygen. Chlorine has more lone pairs. We can also have more than just a single bond. So our atoms share more than one electron pair. O2 has a double bond. Writing it out with lines, looks like this. And you can draw the non-bonding lone pairs anywhere you want. If we wrote this out like with the dots, we might have 4 dots between them. That represents a double bond. I like to use the lines, again, because it's easier. It's also what I'm familiar with. Nitrogen has 3, and so it's that hamburger menu icon. 3 lines, or the exactly equal to sign. if we wrote it out instead with dots, we'd have 6 dots between them. In both of these cases, each of the atoms has a full octet. For the oxygens, we've got 2 bonds, that's 4 electrons. We've got 2 lone pairs, that's another 4 electrons. So they've got 8 electrons, that's our full octet. For our nitrogen, we have 6 electrons in our triple bond, and 2 from a lone pair. That's the same for both nitrogen, so full octets. Questions? So Lewis models can predict the stability of H2O and H3O. So our H2O structure that we saw before, we've got our oxygen in the middle, 2 bonds, 2 lone pairs, oxygen's happy, hydrogen's got its duet from its 1 bond, it's also happy, and by happy we mean stable. H3O, on the other hand, would look 1, 2, 3, 9, 2, 4, 6, 8. We would have to shove an extra electron in there somewhere. And that's not going to be stable. Oxygen now has 9 electrons, or we have to give one of the hydrogens another electron. That doesn't really work. So that's H3O. If we had H3O plus, that would have 1 fewer electrons. So that would look like that. And in H3O plus, our oxygen has 2, 4, 6 electrons from bonds and 2 from the lone pair. It has an octet. The hydrogens each have a duet. So that's going to be more stable than H3O. So comparing our ionic bonds to our covalent bonds, when we were looking at our ionic bonds, they have a lattice, right? They've got positive and negative charges all around them, balancing them out, reacting with them, interacting with them. Our covalent bonds are super, super directional because it's just between 2 atoms. Rather than being in every single direction. So that's going to be a lot weaker because you've got fewer interactions. Our covalent compounds also contain discrete little units rather than that massive lattice of repeating forces. And connecting them are relatively weak forces compared to the ionic positive and negative charges. And so those weaker forces cause our molecules to have lower melting points than our ionic solids. There are 3 forces that get counted in, lumped in with those weak forces. Does anyone remember what those intermolecular forces are? There's 3 intermolecular forces that we learned that would get lumped in with those weak forces. Intermolecular forces. Does anyone remember what those 3 forces are? Any of the 3? Oh. Their dispersion, dipole, and hydrogen bonding. I think that was a couple chapters ago. So we have those forces instead of proper positive and negative charges. That results in weaker forces. It's also quite an oversimplification to just draw our electrons as dots because our electrons aren't really truly shared. There's a little bit of unfairness, I guess, in a bond, in lots of bonds at least. And where those are particularly pronounced is polar covalent bonds. So polar bonds means having poles, like poles on a magnet. It's got a positive side, a negative side. And we have unequal sharing in a polar covalent bond. So one of the atoms is holding the electrons more than the other. So one of the atoms is pulling the electrons closer to it more than the other. That results in a slight negative charge around that thing, whatever it is. In our example here, it's fluorine. Fluorine's a notorious electron hog. So it's pulling the electron density closer to itself. It has a slightly more electronegative environment around it. Hydrogen, because it's losing some of that electron density, becomes slightly positive. Electronegativity is on an arbitrary scale, sort of arbitrary scale. We can think of it as electron pull. A higher number here is stronger. And we've got another one of those 3D charts. So this is showing our periodic table, also kind of askance or askew. Our most electronegative element is fluorine, up in the top right of the periodic table. It's the champ. It's got a value of 4 for electronegativity. That's the highest value. And cesium and francium are on the low end with 0.7. We don't include noble gases because they don't react. And electronegativity generally increases up and to the right. If you have the yellow sheet that's got the periodic table on it, it's got the electronegativity values in the bottom right corner for most of the elements. You should know that fluorine is a 4. And you should know that it increases the closer you are to fluorine. Otherwise, you don't really have to know the values. You'll be provided with electronegativity values in many cases. There's also sometimes ways of coming up with the strength of a bond or the electronegativity difference of a bond without using the electronegativity values. Questions? All right, let's arrange these elements in order of decreasing electronegativity. The four elements that we're looking at are sodium, phosphorus, nitrogen, and aluminum. Where is our highest electronegativity element? Top right, it's what? Fluorine, right? Fluorine is the highest electronegativity, so proximity to fluorine is proximity to power. The closer you are to fluorine, the higher the electronegativity value is. So we're basically going in order of closest to fluorine to furthest from fluorine. Which of these four is closest to fluorine? Nitrogen. Nitrogen is closest, so it should be our first one. And it's only the first one for one of these options. So it's got to be that one. Phosphorus is a little bit lower, so it's going to have a lower electronegativity value. It's further away from fluorine. So phosphorus will be a little bit lower. Aluminum is even further, and sodium's the furthest. There's also a mnemonic for remembering electronegativity order that I think I've memorized a little bit wrong. I don't remember if the I goes here. Or if it goes here. The mnemonic is Fonkel brick ship, which I only remember because it's weird. Yeah, it goes in the first spot. So this might be useful if you, for some reason, need to memorize electronegativity order. Fonkel brick ship will get the job done for you. It was like 2 years ago that I heard Fonkel brick ship. Part of the reason we're learning about electronegativity is to talk about bond polarity. There's 3 options for bond polarity. And it depends on the difference in electronegativity. The delta En, delta being difference, En being electronegativity. And it's sort of on a continuum. We just kind of classify, like, if it's in this sort of difference zone, then we call it this thing. If it's in this other difference zone, we call it a different thing. But these divisions aren't completely fixed. So the scale that we've got here, we've got electronegativity difference on our x-axis. We don't have a y-axis. If we've got a difference of 0 to 0.4, again, it's like roughly 0.4, then we would consider the electrons fairly equally or completely equally shared. We would call that a nonpolar bond or a pure covalent bond. Nonpolar, no poles, we don't have a positive, we don't have a negative. It's evenly shared, it's neutral. If you increase the inequity, those electrons are shared less equally, vaguely from a 0.4 difference to a 2.0 difference. We call this a polar covalent bond. It has covalent bond character. The electrons are definitely shared, but they're not shared equally. again, 0.4 and 2.0 are kind of like our approximate cutoff for those. If it's above 2.0 and up to 3.3, 3.3 because 4 minus 0.7, the lowest value, is 3.3. Anything bigger than 2, though, that's going to be an ionic bond. And the electrons are basically transferred. So we've got basically full positive and negative charges. They're not even sharing anymore. It's just straight up the cation, the anion, a full-on electron transfer. So learning these 0.4 and 2.0 difference marks can be helpful for determining the difference if you've got electronegativity values on hand, like if you've got the yellow sheet, for example. A way of measuring bond polarity is with dipole moment. A dipole moment represented by, I believe this is mu. The funky U from the Greeks. This occurs when we have a separation of charge. So a separation of a positive and a negative charge. It gets this equation. Mu equals Q, where Q is charge magnitude and R is distance. A common unit is the debye, capital D, which has units of coulombs times meters. So C, coulombs for charge, and M, meters for distance, or R, radius. And it's 10 to the minus 29 because the charge is really small and the distance between them is also really small. So you might get to do a calculation with dipole moment on the exam. I'll give you the formula, probably. I mentioned that I threw in some sandwichy word, not sandwichy, some squiggle word basically of like, well, it's sort of, it's kind of, it's not really, nothing's really 100% ionic. And so thinking about a pure ionic bond as being a complete separation of charge, like the electron is wholly given away, that's not really the case. They're actually shared a little bit. And so percent ionic character is one of the ways that scientists have come up with to kind of quantify how much the electron is given away or how much it's shared. So 100% ionic character would mean complete transfer. And a 0 would be fully shared, for example. None of these is 100% ionic. Even for these ones with fluorine involved, fluorine just doesn't quite have what it takes, I guess, to pull away and get a full 100% ionic character, which is our y-axis. Our x-axis is the electronegativity difference. We can see there's like a rough correlation between increasing electronegativity difference and percent ionic character. It's not a correlation of 1, but they're sort of, if you squint, you could, imagine a line that goes through there. And anything on this graph that's over 50% ionic character is considered ionic. So HF doesn't quite make the cut. We still consider that to be a polar covalent bond. All right, we can determine, even without electronegativity values, whether the bond formed between each pair of these atoms is polar covalent, or ionic? What occurs, or what's the characteristics of a nonpolar covalent bond? Are the electrons completely shared, partly shared, or transferred? Completely shared. And what about polar covalent? Are they completely shared, partly shared, or transferred? They're partly shared. They're a little bit hogged by one of the atoms. And then in ionic, are they completely shared, partly shared, or transferred? Yeah, we think of them as transferred, and I think that's only one R. Does anyone remember what the electronegativity difference, the cutoffs are between nonpolar covalent, polar covalent, and ionic? .4, 2.0. Those are kind of our cutoff zones for electronegativity difference. Which of these three pairs is going to completely share the electrons? It is iodine. The reason they have the same electronegativity value, it's the exact same thing, right? It's like if you had two twins playing tug of war. Obviously, it's not like a perfect analogy because twins are different a little bit, but like if they're playing tug of war, you would assume since they're twins, they're about the same strength. Nobody's going to win. It'll just be a dead stalemate forever. That's what is going on here. So that would be a nonpolar bond. What's the case going to be for cesium and bromine? Are those going to have similar electronegativities or different electronegativities? Cesium's all the way on the left side, bromine's all the way on the right side. Different. Are they going to be different enough that we would call it ionic? Probably. Another way that we could figure out that it's an ionic bond is what's an ionic compound made of? A metal and a nonmetal. Cesium is a metal. Bromine is a nonmetal. So we would call that ionic. That usually works. If we had our yellow sheet, cesium's a 0.7, bromine's a 2.8. .7 versus 2.8, that's a difference of 2.1. Definitely ionic. What about for phosphorus and oxygen? They're close-ish to each other. If we think of Fonkel brick ship, oxygen's second, phosphorus is the last one. They're probably not that similar in terms of electronegativity. And indeed, if we look at our yellow sheet, oxygen's a 3.5, phosphorus is a 2.1. Things move quick when you're close to fluorine. So our difference in electronegativity is 1.4. We would call that a polar bond. Questions about those? All right, here's those steps that I was alluding to earlier, like before we just made a bunch. Here's how we put together Lewis structures. Our first step, we want to get the correct skeletal structure. How are the atoms arranged relative to their neighbors? So we're going to lay out the atoms. Hydrogen atoms are always terminal because they only form one bond. And they only form one bond because they only need a duet. One bond, two electrons have a duet. And we're going to tend to put more electronegative atoms in terminal or exterior positions. Another thing that we'll often consider for this correct skeletal structure is symmetry. More symmetrical molecules are more stable. So if we can get left-right symmetry, if we can get top-bottom symmetry, that's also beneficial. Then we're going to calculate the total number of electrons by adding up the valence electrons. If we have a charged compound like an ion, then we need to subtract electrons for charge. So that'd be an extra thing that we add in. If we have a 1 positive charge, that's 1 less electron, since electrons are negatively charged. And I feel like we're skipping a step here, but we're also going to distribute the electrons among the atoms, with our goal being octets. We also need bonds to connect everything. I will often do 1 bond between everything to connect all the atoms before I start adding in the extra valence electrons. And I'll usually add the electrons from the outside and work my way in. You don't necessarily need to do that. If any of our atoms doesn't have an octet at that point, then we can form double or triple bonds, thereby sharing more electrons. To get up to octets. Okay, we want to write the Lewis structure for CO and H2CO. Our first step, we need to have the atoms. Let's write out the atoms. For CO, we just have 2 things. You can't get them wrong. Don't put them on top of each other because it looks confusing. We're working in 2D space, not 3D space. How many valence electrons do we have access to? It's a little harder when you don't have a periodic table. There's just the little one in the back of the class. Carbon has 4, oxygen has 6, so it's 10 total. So we've got 10 valence electrons. We need to connect them. That costs 2 electrons. So 2 bonding electrons between them. We've got 8 remaining electrons to place. I use this notation because that's what I use for my 3As, so I'm just used to it. To place the 8 remaining electrons, we've got 2 places we can put them. Let's give 4 to each. Doesn't really matter how you place them. And now we want to see, do we have octets? We don't have octets. How many valence electrons does carbon have? Here. 2, 4, 6. That is not enough, right? Oxygen has the same situation. So we're going to need to form some extra bonds. Let's move those 2 electrons in. I'll just cross them out. So now we have 4 in the double bond, plus 3 on each the carbon and the oxygen. That's 7. Not quite enough. We're going to need another round of electron infusion. And if we do that, now we've got a triple bond between carbon and oxygen, plus a lone pair on each. They've got their octets. We did it. Questions about putting together the Lewis structure? All right, next up, Lewis structure for H2CO. To get symmetry, I'm going to put carbon in the middle and the hydrogen on either side of the carbon, rather than putting it all in a line. I also know what the structure is, so I have that advantage as well. Counting up our electrons, carbon 4, oxygen 6, 2 hydrogens means 2 times 1 electron, 2. So we've got 12 valence electrons. Then we have to put 3 bonds to get everything connected. That means we have 6 remaining electrons. How many electrons can we put on oxygen? How many more electrons? We can put all 6, right? So I'm just going to put all 6 of those electrons on oxygen. Let's check our octets. Hydrogen's happy with 2. It's got 1 bond, it's got 2. Oxygen has its octet. Carbon has 3 bonds. 3 bonds is 6 electrons. Carbon is not happy. Carbon's not having a good time. How can we get more electrons to carbon? Yeah, we're going to put a double bond in there. So that's going to turn this structure into this. Something like that. So now we've got a double bond between our carbon and our oxygen. Carbon has 4 bonds. Oxygen has 2 bonds and 2 lone pairs. So those both have their octets. Hydrogen will have their duets. That's a good Lewis structure. Questions? For polyatomic ions, we get to add 1 electron for negative charges and subtract 1 electron for positive charges. That was mentioned earlier. And we write the Lewis structure within brackets with the charge in the upper right-hand corner outside the brackets. For example, ClO minus. Our skeletal structure, ClO. Chlorine has 7 valence electrons. Oxygen has 6 valence electrons. It has a 1 negative charge. Are we adding or subtracting an electron? Yeah, we're adding 1 more electron to get us to a total of 14 valence electrons. To start off with our Lewis structure, we need to connect it. So we'll put in 2 bonding electrons. That leaves us 12 remaining electrons. We can distribute those evenly, 6 to each That's all of our electrons placed. If we check for octets, we've got 3 lone pairs, 6 electrons, plus the 2 that are shared. Each of these has its full octet. Is this a good Lewis structure? It's not a good Lewis structure. And you know that because, well, I asked, and that's weird. Why isn't it a good Lewis structure? Yeah, we have 1 extra electron in here. So we need brackets, we need the 1 charge in the upper right-hand corner. Now this is a good Lewis structure. Some molecules also have more than 1 valid Lewis structure. For example, O3. These are in a line. We could have that Lewis structure. We could also have its mirror image. How do we choose? If you come to a fork in the road, take it. So what we do here is instead of choosing, we say, no thank you, I don't want to make a choice today, I'll take both please. And we do that by writing that double-headed arrow between them. So this is how we represent it in Lewis theory. In reality, it's a hybrid of those 2. So we have equally valid Lewis structures with arrows between them. The double-headed arrows to show that it's switching back and forth between the 2, or it can be both. So the actual structure, the way that it really exists, again, is a hybrid. And we call it a resonance hybrid. It's similar to if you take 2 cats and breed them together, you would get a cat that is kind of hybrid with the characteristics of the 2 parent cats. So our 2 structures that we had, right, the ones that I drew out earlier, In reality, it's like a 1.5 strength bond between each of the oxygens. Instead of a single bond and a double bond, it's like a 1.5. They're sharing those electrons. What's actually happening is in our Lewis model, our electrons are localized. They only sit in one spot. In reality, they're often delocalized, meaning that they can move across a region, or they're evenly shared across a region. And this causes something called resonance stabilization, which if you take organic chemistry, you'll learn all about. We might even talk about it a little in this class. Okay, since I'm running out of battery on my iPad, and to give you a little bit of time to do stuff, write structures for 2-, please include resonance structures. All right, hopefully enough time for you to come up with your resonance structures for NO2-. To get these to be symmetrical, we're going to put nitrogen in the middle. Nitrogen has 5 valence electrons. Each of our oxygens has 6, so 2 times 6 electrons for 12. And we have a 1- charge, so we'll add one more electron. That gives us a total of 18 valence electrons. To get everything connected, we need to start with at least 2 bonds. That leaves us 14 remaining electrons. We don't have room on our oxygens to put all of those, but we put 6 on each. That is 12. That leaves us 2 more electrons. That we can put on the nitrogen. So all of our electrons have been placed. And now we need to check our octets. Checking for octets, our oxygens are both content. They've got 3 lone pairs and 1 bond. 3 lone pairs is 6 electrons, 1 bond is 2 electrons. That's a total of 8 electrons. Our nitrogen, however, is sad. It only has 6 electrons. In order to get our nitrogen to not be sad, we need to give it money. Electrons. So we have a choice to make. We can add a lone pair from the left side, or we can add a lone pair in from the right side. And how to make this very difficult decision? The answer is we don't. We don't make this decision. So we can draw the case adding in on the left. Boop. And we can also draw what it looks like if we add it on the right. So this is what those would look like. What are we missing? Arrows, brackets, charges. So our brackets with our negative charges, and the arrow with 2 heads showing that we've got resonance structures. Questions about putting that together? Okay, if you do have any comments or questions, I'm happy to stick around and basically do office hours here. I'll end the recording.